Hello there. This video is intended to be a supplement to elementary statistics, and specifically, we're going to be covering some of the math review topics that will be essential to your success in this class. Now, I should note that many of you may already be familiar with the topics that we're going to be reviewing in this video, and so as a result, you should feel free to fast forward, to watch this on a faster speed, maybe the double speed. Or you can certainly use in the video description the chapters that are broken down based on the topics. If you need a refresher, you just want an idea of the questions that are going to be asked on the homework assignments that cover these particular topics. Now, the topics in particular that we're going to be looking at involve 7 distinct units, topics, concepts, however you want to think about them. The first deals with our place value, along with reading, writing, and rounding numbers. The second deals with fractions, decimals, proportions, and ratios. The third is operations. The fourth, solving equations and formulas. The fifth is set theory, specifically the intersection and union of sets. The sixth one is translating English to mathematics. And lastly, plotting points, lines, and equations of a line. So once again, please feel free to use the bookmarks in the video description below if you need to just simply fast forward to the concept that you need to review in particular. The first concept that we're going to look at deals with our place value system and reading and writing and rounding numbers. So this is a rather important set of skills that we often use every day. So we have to remind ourselves how the place value system works. So on the screen, you'll notice that we have a bunch of dashes, a comma, and what appears to be a period. And what we need to remind ourselves is how exactly we read numbers. Well, truth be told, you can think of reading numbers almost as if they have names. In fact, a first and a last name, just like you and I have. So we have the first family of numbers, if you will. We call them the no name, and that'll be clear in a moment when we look at an example as to why we call this the no name family. Next, we have the thousands, the millions, the billions, the trillions, and it keeps going. There are more numbers, more place values that we can study, but trillions will be the extent, at least, of this discussion. Now, you'll notice that each of the families is separated into 3 digits, and they are separated by the comma. So the comma is very, very important in helping us to read numbers. Now, there's something else I want to point out to you, which is the decimal. The decimal is also important. And the way we read the decimal is using the word and you'll see that in a few minutes. So let's try to understand this in the context of an example. But before we do that, let's look more specifically at the actual place values. So we may have learned in grade school, we have the ones place, the tens place, and the hundreds place, and that those first 3 place values, remember, they don't have a last name. Okay, so we just literally would call it the ones, the tens, and the hundreds, and that's it. If we move beyond this, what you'll notice is that the ones and the tens, hundreds repeats itself, but then you include the last name. So in this case, the next family of numbers for the place value would be thousands. And then we would have 1 million, 10 million, 100 million. And then we would repeat for billions and trillions. So that process all repeats. You just have to remember then what specifically are the last names. In other words, the no name, the thousands, the millions, the billions, and the trillions. Now, on the other side of the decimal, we have the tenths, the hundredths, the thousands, the 10,000s, and I'm about out of room, but we have the 100,000s. Okay, if you're wondering what would come next, it would be the millions, 10 millionths, and 100 millions. Now, you should notice that when we are on the right side of the decimal, all of those place values, they have the THS on the end, okay? So make sure you do emphasize that, and if you're writing out the number, make sure you do include the hundredths, that THS, because it is different than hundreds. Very, very important. Now, reading numbers really comes down to reading 3 digits at a time. So if you're comfortable reading 3-digit numbers, you're going to be fine with reading any kind of number that we give you, no matter how big it may look. Okay, so you just have to remember what the last name is. So let's try this number. Let's see if we can read this number. What exactly would this sound like? Well, we begin on the left side. We always begin from the left side and work our way to the right. So you look at the first family. Now, what's nice is the comma helps to separate separate that. So the first number I see, the first 3 digits, well, sort of 1 digit, but we see is 4. Okay, well, what's the 4's last name? 4 trillion. Okay, what's next? 305 billion, 941 million, 5,415, and 477 10,000ths. And so that is how you read the number. And there it is in English, fully written out for you if you need to take a look. And I did put emphasis on the and, that's why it is capitalized to draw your attention that it is the decimal, okay? Now we will talk about how to read decimal numbers a little bit later. So if you didn't really catch how I got the 477 10,000ths, don't worry, we'll come back to that. For now, just make sure you're focusing on the no name, the thousands, the millions, the billions, and the trillions families for now. All right, here we are. How do you read decimals? We're at it already. Okay, now what we do to read decimals is really simple. What we do is we simply read the number and then we use the place value of the very last digit. In other words, the digit that's on the right side. So if I asked you to read this number, this would simply be 5, and then we look for what the place value is. In this case, it would be tenths. So this would just simply be 5/10. Now, if we put an 8 here, okay, now the question is, well, what number is that? Well, that's 58. Okay, 58 what? Well, we look at what the rightmost place value is. This would be hundredths. So this would be 58 hundredths. All right. How about this one? Well, I read that as 580. Okay, 580 thousandths. Okay, 580 thousandths. How about this one? Well, I would read this as 5,809 10,000ths, since that 9 is in the rightmost digit, the 10,000ths place. Now, what happens then if I put a number on the left side of the decimal with some values that are on the right side? Then how do we read this? Well, again, we work left to right. So I see that that 4 is in the ones place, so it's simply 4. We read the decimal as and, so 4 and 5,809 10,000ths. And there it is on the screen written out for you. So hopefully that's pretty straightforward in how we read a number. So take your time with it, write out the place values if you need to with the families so that you're able to read the numbers. And really it comes down to, again, reading 3 digits at a time. And then when we read the decimals, literally read the number and then you take the rightmost place value. Now, another aspect is you're going to have to be able to do some things with these numbers. And so in order to get us there, whatever this means, what do we need to do with these numbers? Before we can get you there, we need to make sure that we understand the place values a bit more carefully. All right, so we have this number on the screen here, and I'm reminding you of the families. We have the millions, the thousands, and the no name. And what we need to do is to figure out what digit is in the ones place. All right, so the first thing we need to do is figure out where the ones place is. There it is. Okay, and I noticed that the 4 is in the ones place. So the answer to that question is 4. What digit is in the 10 millions place? Okay, well, I know where the millions family is, and I remember that they're always grouped as ones, tens, and hundreds. And then, of course, the family's last name, the millions. So that 0 there, where the arrow is in the tens millions place. So this particular answer would be 0. What digit is in the tenths place? So I noticed the THS, which tells me I'm on the right side of the decimal. Okay, that's great news. So which place is it? Well, it's actually the first one, if you remember your place value for decimal. So this would also be the answer of 0. That's the digit that lives there. And then we want to write this number in English. Okay, that's exciting. So how would this work? Well, let's remember, we read it 3 digits at a time, and then we remember the family last name. So in this case, we would begin with 304,008,984 and 1,000th. Okay, 1,000. You notice I hesitated there. I needed to count my decimal places on the right side of the decimals there. So tenths, hundreds, thousandths. That 1 is in the thousandths place. So 304,008,984 and 1,000th. So that's what that number looks like. Okay, what we need to do now is to write each of these phrases that are given to us in English. We want to be able to use them writing and using numerals. So this means the actual digits. So let's suppose we were given 503 and 1700. So the first thing that I notice is the word and. So I know there's a decimal. Okay, and there's a further clue that I know this. If you look, we have the THS. So I know that I'm going to have to be dealing with some decimals here. Okay. Now I also notice that I'm dealing with 503 and there's no last name. I don't see thousands, millions, billions, or trillions. So I know I'm dealing with the first three place values on the left side of the decimal. Okay, so there they are, ones, tens, hundreds. There's my decimal. And since I'm dealing with hundreds, I know I'm going to have tens, hundreds, two decimal places. So they're written there for you. And we take the number 503, there it is, and is again denoted by the decimal, 1700ths, each of those two decimal places. Next, 16 thousandths. So this one is interesting, 16 thousandths. I don't see the word and, so I know I'm not dealing with at least a whole number and a decimal. I know I'm going to have a decimal because I see the THS that goes along with that. Okay, and I know the thousands was 3 decimal places to the right of the decimal. All right, so then how does this work? Well, there's the 16. So we have to go as far right as we can with those 3 decimal places. Okay, so there it is, 16. So what goes in front of the 1? Well, you need a placeholder, and the placeholder here would be 0. Now, some of you might be thinking, well, what if we wrote this? Wouldn't this be 16 thousandths? And the answer is no. That's actually 16 hundredths. Very big difference. How do I know it's 16 hundredths? Look where the 6 is. It's in the hundredths place. It's not in the thousandths place like we wanted. So be careful. A little tricky here. Okay, they are 2 different things. And finally, we have 39,017 and 7/10. Okay, oh my goodness. So this is a pretty short number, but it looks pretty big, at least with the millions place. All right, so I know I'm going to at least need out into the millions. I see the word and, so I know I need a decimal. And we're dealing with the tenths place. So this is 1 place beyond the decimal to the right. All right, so we begin 39 million. So there's the 39. It lives in the millions family. Okay, and then the next one we have is 17. How do I know that? Well, there's a comma. The comma tells me here comes the next family. Okay, and it happens to be the no name family. That's what 17 looks like. And then there's the 7/10. Okay, now what do we fill in between there? It's easy. You put your zeros. So there's the number 39,017 and 7/10. Hopefully everybody's still with me here. Now, what is the point of all this exercise? What is this leading us to? Well, we have to be able to round numbers, okay? Truth be told, guys, in the homework, it's going to ask you, here's an answer, please round to the nearest hundredth place or round to 4 decimal places. You have to be able to do the rounding. So this is sort of what we're leading up to here. So very, very important. Now, to round numbers, you have to know your place values. There's no getting around that, okay? Now, the process is actually very simple. So we've got a few steps for you. So the first thing you do is you identify the digit you are looking to round, okay? So if it tells you round to the thousands place, you need to know where that is. Then what we do is we look at the digit that's to the right of that place value, all right? Now, if that digit is 5 or more, then what we do is we actually round up. If it is 4 or less, we keep the number the same. So the number that we're interested in rounding, we would keep the same. Okay, so let's look at this example. 4,925 and 1,074 10,000s. We need to round this to the nearest hundredth, all right? So there's the number again. So the first thing we do is we identify where the hundredths place is. There it is, it's the 0. What I do is I looked at the number that's to the right of that, which is 7. And so I ask myself, is 7 more than 5? It is. We round up then. So that 0 becomes a 1. So my answer here would be 4,925 and 11 hundredths. Okay, 11 hundredths. Let's look at another one. So the same number. This time we want to round thousands. Okay. So we look for where the thousands place is. There it is. There's the 4. So the number we look at to the next to it, to the right, is a 9. 9 is more than 5. We get to round up again. So the 4 becomes a 5. My answer then is 5,000. So some people get confused. What happens to the other digits? Well, they become zeros. We're rounding this up. That's the whole idea of rounding. Kind of makes the number a little easier, Let's look at rounding this to the ones place. Okay, 4,925 and 1,074 10,000s. Where's the ones place? There it is, it's a 5, okay? We look at the digit that's to the right. In this case, it's a 1. Now, some people might wonder, well, what about the decimal place? We don't care. It's irrespective, independent of the decimal place. Now, the 1 is clearly less than 5, so it's 4 or below. So we have to leave the 5 alone, okay? So that 5 is going to remain a 5. So the answer here, rounded to the nearest ones place, is 4,925. So this concludes the discussion on this segment involving place values and rounding and reading various numbers. Our next discussion deals with fractions, percents, decimals, proportions, and ratios. Try saying that 20 times fast. I bet you can't do it. All right, but what I bet you can do is the math that's contained in this particular unit. So let's take a look. All right. First, we need to go through some definitions, all right? So that's a good place to begin. Some of you might be wondering, what do all of these things mean? Well, here's what I want you to do. Keep things very simple, all right? Let's not confuse and muddle things. Fractions, what I want you to walk away with, they're simply numbers. That's it, okay? Somebody asked you, what's a fraction? It's a number. The top number is called the numerator, and the bottom number is called the denominator. We give them some special names. Now, a percent, what I want you to think of is percent means hundredths, okay? So 35% literally would be 0.35, or literally as a fraction, 35 hundredths, 35 over 100. So pretty easy. And we'll talk actually about how to convert percents to decimals and fractions. So you actually get a little preview right there. Now, often people wonder, what exactly is a ratio? What is a proportion? What's the difference between the two? So ratios are actually comparisons, and they're comparisons between two categories, two different categories. So sometimes people will talk about the ratio of men to women or women to men, depending on your perspective, okay? Or the ratio of maybe various colors, or the ratio of baseball players to football players, or the ratio of freshmen to sophomore. So there are a number of different contexts, but the key here is it's comparison between two different categories. Now, sometimes ratios can be expressed as fractions. Sometimes that's how we like to write them. Okay, so there's a little bit of relationship here to fraction. Now, a proportion is a bit different. A proportion can be expressed as a fraction, a decimal, or a percent, depending on what we're trying to do, what we're trying to look at here. But a proportion differs from a ratio in that it only focuses on a single category, and more specifically, a quantity of that category, okay? So what are we talking about? Well, something like this, the proportion of college students who watch baseball. So to figure that out, what we would do is have to go count the number of college students who actually watch baseball, and we put that over the total number of college students. Pretty straightforward, at least I hope it is, okay? So there's a little bit of a difference here from ratio. Ratio, we're comparing two different categories. Proportions, we're only comparing a single category. And we have a quick fact, just in case, because sometimes this comes up and people get a little confused. So if we have any number over the number 1, the answer here is that number. So what am I talking about? Well, if you have something like 7 over 1, that means 7. Negative 9 over 1, that means negative 9. 0 over 1, this would be 0. So this would continue. So there may be instances where we either want to write this integer, this 7, this negative 9, this 0 as a fraction, or we get something that's over 1 and we can simplify it a bit easier. So these are the fun facts to keep us going, but make sure you pay attention to these definitions because sometimes they may come up in the problems, and we want to make sure that you understand what exactly they mean. Now, the next topic is going to be dealing with converting and simplifying fractions, okay? So sometimes in the homework, they might ask you to express an answer as a simplified fraction. We have to know how to do this. Now, you also might be asked to do some converting of fractions in order to actually perform some operations, which, by the way, is coming, okay? In a few minutes, we're going to be looking at, or at least in another segment of this video, how to do some operations on fractions. And so you might have to get a common denominator, for example. So how exactly do we do that? Well, the good news is to convert any fraction, we multiply by some form of 1. Okay, so what do I mean by a form of 1? Well, something like 4 over 4, 19 over 19, 341 over 341, etc. The list goes on. So there are multiple versions of this, these forms of 1. Okay, well, let's first convert 3/5 to 20th. So how do I do this? Well, what we do is we write the setup as 3/5 is equal to 3/5 times something equals something over 20. Now, the reason I know that denominator is a 20 is because it tells me we're converting to 20th. So what I need to figure out then is what's the form of 1? So the easy way to do this is to look at what is 5 times what equals 20. The answer to that is 4. So the 4 over 4 here is actually the form of 1 that we're multiplying by. So we do the numerator and we notice that 3 times 4 is 12. So 3/5 is equal to 12 20ths. So we call these equivalent fractions because they are indeed equal. Okay, 12 20ths might look a little different, but it's still 3/5. Okay, how do I know that? Well, we have the equal sign. Okay, so 4 over 4 again was the form of 1 that we used here. Now, to simplify a fraction, we actually do this process in reverse. What we have to do is we have to factor both the numerator and the denominator, and instead of multiplying by a form of 1, we're actually removing it. Okay, that's simplifying the fraction. We don't like to use the word reduce because that implies the fraction's smaller. That's not what's happening here. The numbers might be smaller, the numerator and the denominator literally may be smaller, but the fraction itself is not reduced. Okay, so that's why I try to avoid that word. We say simplify. So it's the inverse of the process we just performed. So if we wanted to simplify 36 over 63, what we would do is I would factor 36 and 63. And the way I chose to do that was 3 times 12 and 3 times 21. There's my form of 1, 3 over 3. Boom. What's 1 times 12 over 21? 12 over 21. Now, some of you might be looking at this and say, hey, I can simplify that. I know, I just did it. Okay, we notice we can factor 3 again. So 3 times 4, 3 times 7. There's my form of 1, 3 over 3, and I'm left with 4 over 7. Now, 4/7 can't be simplified anymore. There's no other form of 1 aside from 1 over 1, which is boring, but there's nothing else I can factor out of both of those. So that's how we know the process is done. Now, some of you might be looking at this and say, well, couldn't we have factored this as 9 times 4 and 9 times 7? And gotten 4/7 in one step? My answer to you is yes. Okay, some people see it really quick. They can see that factorization really nicely. Some people need to do a couple of steps. I'm okay. It doesn't matter to me how you get the answer as long as you get there and you simplify it. So these are the two processes. Converting fractions, we multiply by a form of 1. To simplify a fraction, we have to factor and remove the form of 1. So those two things you may be asked to do in the computations to come. The next piece to this is we have something called a mixed number. Okay, what is a mixed number? Well, it's where we put an integer and a fraction together. So an integer is a positive whole number or their opposite. So something like 8 would be an integer, -8 is an integer, 115, -3007, those are all integers. So when we put an integer and a fraction together, we get this mixed number. And there are two examples on the screen here, 7 and 2/3. Notice how I read it, 7 and 2/3. That's what that word and connects the integer and the fraction. And then the other one here, -52 and 31/99. Okay, so that's how we read these two mixed numbers. Now, to convert a mixed number to a single fraction, there is a process. I hope you all are sitting down. Here's the process. Number 1, we multiply the denominator by the integer. Then we add the product from step 1 to the numerator. We take the result from step 2, and that becomes your new numerator, and the denominator remains unchanged. So what the heck does this mean? Well, let's look at an example. So we need to convert 3 4/5 to a single fraction. So the first thing we do is we take the denominator, which is 5, and we multiply by 3, which in this case is the integer. So 5 times 3 is 15. We take the 15 and we add that to the numerator. The numerator was 4. So 15 plus 4 is 19. That 19 becomes the numerator. Now, what's the denominator? Well, the denominator remained as a 5, so that denominator is going to stay as a 5. It remains unchanged. So the moral of the story is 3 4/5 is equal to 19/5. So this is how we convert mixed numbers to a single fraction. Now this fraction, some people say, well, isn't this an improper fraction? And yes, okay, some people may label it that because the numerator is more than the denominator. Some people like to call it a fraction greater than 1 or an improper fraction. So whichever you wish to use. Now, let us suppose we were given a single fraction and we want to convert it to a mixed number. Then we have to use long division, okay? So again, we're called improper fractions if you want to think about it that way. So I give you a little bit of a formal definition, which is basically what I just said. So let us suppose we have 7/5. This is an improper fraction as an example. Okay, let us convert 16/3 to a mixed number. How do we do this? All right, well, we use the long division. So the numerator becomes the dividend. In other words, that 16 goes into the division house, if you will. The denominator of 3 is the divisor. So you divide 3 into 16. That goes 5 times. 5 times 3 is 15. We subtract, we get a remainder of 1. So the quotient, that 5, becomes the whole number. Okay, or integer. The remainder becomes the numerator, and the divisor there, that 3, becomes the denominator. So 16/3 becomes 5 1/3. So the 5, the quotient, becomes the whole number. The numerator there is the remainder of 1, and the divisor, being 3, is the denominator. So that's how we convert. We have to use long division in that process. Okay, now the next piece to this is looking at converting between decimals, percents, and fractions. So this is important because this is something that you will have to do in some of the online homework and other aspects of your assessments potentially in elementary statistics, is being able to convert between all of these, especially depending if there are specific directions that ask you to express the answer in a specific way. All right, so let's start easy and work our way up here. So to convert any decimal to a percent, we simply multiply by 100 and we add on the percent sign. Everyone asks why. Easy, percent means hundredths. So we remember that when we multiply by any power of 10, we move the decimal to the right by however many zeros are in the power of 10. So in our case, we're dealing with 100. So I see 2 zeros there. 100 happens to be a power of 10. So we move the decimal to the right 2 place values, and we'll look at some example. So let's convert 0.39 to a percent. So what would this look like? Well, we move the decimal place, okay, decimal 2 places to the right. So we take that decimal and we move it, we get 39, we throw the percent sign on there, and we're done. 39%. Some people will write it as 39.00%, that's fine, or 39%, either is fine. Okay, what happens with 0.4165 to a percent? Well, we proceed the same way. We move the decimal 2 places to the right. So that would give us 41.65. We throw the percent sign on. So we get 41.65%. Okay, no big deal. We can have a fraction of a percentage, perfectly fine. How about 0.0071 to a percent? Okay, same way, we move that decimal 2 places to the right. So this would give us 0.71%, 0.71%. So again, a fraction of a percent. So this is less than 1%. Sometimes percentages work that way. Okay, now how do we convert a percentage to a decimal? Well, we simply reverse the process that we just looked at, okay? So instead of moving the decimal to the right 2 places, to go the other way, we move it 2 places to the left. All right, so what are we talking about? Well, let's say somebody says 53%, convert this to a decimal. Okay, I write the number as 53, I drop that percent sign. Again, working the process we just did in reverse, drop the percent sign, there's 53. Move the decimal 2 places to the left, 0.53. How about 22.1% to a decimal? Okay, same idea. Move the decimal 2 places to the left. So 22.1%, 2 decimal places to the left, becomes 0.221. How about 3%? Same way, okay, 3% moves the decimal 2 places to the left. We're left with 0.03. And finally, 0.008%. So this is a really small percentage. Okay, same idea. 2 decimal places to the left leaves us with 0.00008. Okay, so a very, very small decimal. But hopefully you get the idea. So to convert that percent to a decimal, move the decimal 2 places to the left. So inverse of the other process. Okay, now to convert a fraction to a decimal, here's the good news. You can use your calculator, okay? Or if you like, you can use long division. So I'm gonna talk you through this using the calculator, since in this particular course, you're able to use a calculator. So if you wanna get your calculator, pause the video and go ahead and grab it so you can follow along with me. Okay, now we have to understand that some decimals behave in different ways. So there may be some decimals that terminate or stop. There are some that are just going to repeat, and there are some that are just going to go on forever and don't repeat. They just go on forever. Okay, seemingly random. So let's convert 4/5 to a decimal. Okay, so on your calculator, you're going to push 4 divided by 5, and what should come out is 0.8. And in this case, you'll notice that this decimal terminates, so it stops. So pretty simple. If you were to convert 7/9 to a decimal, you're going to type into the calculator 7 divided by 9, and what you should come out to see is 0.77, and actually you see a whole bunch of 7s. This is known as a repeating decimal. The notation we often use for the digit that repeats is we put a bar above it, and what that tells me is that this decimal repeats. More specifically, it tells me the digit that's repeating. So in this particular instance, it's the 7 that is repeating. So that's how this is expressed. Now, to convert a fraction to a percent, we first have to convert it to a decimal, which we know how to do because we just did it. We take the decimal and we move it 2 places to the right. So what we're actually doing is combining 2 processes that we've just learned. Okay, so let's convert 4/5 to a percentage. So what we do is on the calculator, we type in 4 divided by 5, and what should come out is 0.8. You might say, well, this looks familiar. I know, we just did it. Okay, so there it is as a decimal. Now what we need to do to get the percentage is we move the decimal 2 places to the right. So you get 80%. If we want to do this with 7/9, it works the same way. Okay, 7 divided by 9 into the calculator, and out comes 0.777. We know that that's going to keep repeating. That's okay. That's why the ellipsis is there, the dot, dot, dot. Moving that decimal place 2 digits to the right, we get 77.7%. And you'll notice I put the bar above the 7 that in the 10th spot, letting you and I know that that decimal continues. It repeats. Now let's get a little interesting here. Let us suppose we wish to convert 19/31 to a percentage and we want to round it to the nearest 100th of a percent. All right, so how does this work? Well, we enter 19 divided by 31 into the calculator, and what comes out is 0.612903. Okay, and what we need to do is we need to move the decimal 2 places to the right, so 61.2903%. Okay, so first express that as a percentage. And now I need to think about how to round this. All right, so we have to remember the 100th place, the digit there is the 9. Next to the 9 is a 0. Okay, the 0 means what? Well, it means the 9 remains unchanged. And so this particular percentage rounded to the nearest 100th is 61.29%. Okay, 61.29%. To convert a decimal to a fraction, well, we have to recall our decimal place values. All right, so there they are as a point of reference for you, in case you forgot them, the tenths, the hundredths, the thousandths, 10,000s, 100,000s, and look, I added a few more, millionths and 10 million. So we didn't have those on the large place value that we looked at in the earlier segment, but here they are. Okay, so here's how we do this. This is pretty simple. It says the numerator is the number itself, okay, and the denominator is the place value of the rightmost digit. So how would this work? So here's this number, okay, 0.5601. So we would read this as 5,601 10,000ths, if you remember from the earlier segment. So we take the literal number, which is 5,601, and we put it over something. So what do we put it over? Well, the denominator is the place value of the rightmost digit. So the rightmost digit here is the 1. And that's in the 10,000ths place. Think about how I just read the number, 5,601 10,000ths. There it is, 5,601 10,000. So you see the connection between how I literally verbalize it to you and then what it looks like as a fraction. So these are kind of nice and easy to read and also express as a fraction, as long as so there's a good connection there. 5,601 10,000. So that 10,000th is the denominator. The next one here is 0.100005. Okay, so how do we read this particular number? Well, this is 100,005. Okay, what? I think this would be millions. Yes, it is millions. So 100,005, and I was counting the decimal places. There are 6 decimal places, which is the millionths place. So 100,005. 1 million. So this is a pretty interesting looking fraction. Now, to convert any percentage to a fraction, we simply drop the percent sign, write the resulting number as the numerator, and the denominator is 100. Now, everyone asks, well, why? Easy. Percent means hundredths. Okay, so we did this already. I think the example in what we were looking at when I defined what a percentage was 35%, and I think I gave you what that looked like as a fraction and as a decimal. So convert 48% to a fraction, real easy. 48% is simply 48 over what? Well, it's 48 over 100, because that's exactly what a percent means. It means hundredths. So the denominator is always 100, regardless of what the percentage is. Okay, another example here, 81.36%. What does this look like? It's 81.36 over 100. Why? Percent means hundredths. Now, some people get a little weirded out because the numerator has a decimal in it. It's okay. It's just the way it works out here. Okay, 81.36%, 81.36 over 100. No big deal. Okay, just what are fractions? They're numbers, so not a problem. All right, we've got an application. This is a long segment, I know. So fractions in application. So what is the application? Well, let's give you a scenario and let's ask you some questions that follows. So it says Tom surveys his class and finds that among 42 students in the class, 19 really love the Detroit Red Wings. What proportion of students in Tom's class love the Detroit Red Wings? So there's a key word there, proportion. Okay, so I remember the definition. The definition said that it was sort of this comparison of a single category. So we had to consider the count, okay, of how many people do something or what the objects do over a total. Okay, so what is the total here? Well, the total here is 42 students in the class. So that's going to be my denominator. Okay, now what do we care about? Well, what we care about is the proportion or the number here who love the Detroit Red Wings. Okay, well, 19 love the Detroit Red Wings. Okay, so that's going to be easy. 19 out of 42 is what we're going to be looking at here. So 19 students love the Detroit Red Wings out of the 42 in the class, 42 being the grand total. Okay, so you will have some questions that will ask you to figure out what the proportion is, so make sure you're paying attention. Oh, and as a decimal, sometimes we might ask you this as well. So what is this as a decimal? Well, 19 divided by 42 in the calculator, 0.452380. And as a percentage, we know how to do this. Move that decimal 2 places to the right, 45.2380%. And I think I'm out of space. Otherwise, I would have asked you to round it maybe. But you can see it's about 45.238% of the class loves the Detroit Red Wings. Okay, here's another one. Let's suppose it was found that 89% of newspaper readers enjoy coffee in the morning. Out of 100 readers, how many would you expect to enjoy coffee in the morning? Okay, so 89% love coffee while reading the newspaper. Newspaper readers enjoy coffee in the morning, and out of 100, how many would you expect to enjoy coffee? Well, this is pretty easy because percent means hundredths. So 89% as a fraction means 89 over 100. So if we had 100 newspaper readers, 89% means 89 of them out of the 100 are going to enjoy coffee in the morning. So pretty straightforward, pretty easy in this particular case. Okay, so we could also extend this to say, well, for every 100 newspaper readers, we would expect 89 to enjoy coffee in the morning. So if somebody gave me another 100, well, 89 of those, another 100, 89 of those, etc. So that's the idea behind a percentage. All right, still more to go. All right, to compare decimals. So this is important. This is something that we'll need a little bit later on in the course. Okay, so we going to have to make some comparisons between decimals, especially when we're trying to understand which is closest to certain numbers. Okay, so please pay attention. All right, so to compare decimals, we line their place values up. So this makes the comparisons easier. And then what we do is we work left to right to compare the digits in each place value. So in this particular case, which is more, 0.34 or 0.71? Now, some of you might say, well, this should be very obvious, isn't it? Well, let's make sure that we follow our rules here, because sometimes they're not quite as obvious. So here we are, we line them up. We make sure all the place values and the decimals are lined up. And I compare the first place value. Okay, now the first place value technically would have been the ones place, but I'm going to be honest with you, it's boring. They're both 0, so that doesn't help me. So I go to the next place value and I notice a difference. That happens to be the tenths place. You notice we have 3 and 7. Well, 7 is clearly larger than 3. So 0.71 is clearly the larger number, or 71 hundredths is the larger number. Okay, how about this one? 0.04556, 0.0455. Okay, which of them is larger? So I told you, not quite as obvious. All right, so here we go, we line them up, and we notice we have an issue. One of them has an extra digit. Not anymore. There it is. Now they're evened up. Okay, so sometimes you might have a number that has an extra digit. What we can do is we can simply put a 0 on the end. This does not change the number when we're dealing with decimals, only when we're dealing with decimals. Okay, it does not change the number. Now, if you'll notice, you start comparing the place values, you notice they're all the same with the exception of the last place value. Now we have a difference between 6 and 0. All the other ones were the same, 0, 0, 4, 4, 5, 5, 5, 5. Here we have 6 and 0. Well, okay, 6 is clearly more than 0. So 0.04556 or 4,556 hundred thousandths is bigger than 455 ten thousandths. All right, here's one. Which is greater, 51.34% or 0.0455? So we have a bit of an issue, okay? One's a percent, one's a decimal. Okay, so we need to convert one to match the other. So it's up to you how you choose to do that. So we could convert the percent to a decimal, or we can convert the decimal to a percent. It's up to you. Okay, so what I'm going to do is the latter. I'm going to convert 0.0455 to a percent. And to do that, we move the decimal 2 places to the right. I know that because I paid attention to myself a few minutes ago in this segment. So that gives us 4.55%. Okay, we line them up. Okay, well, put a 0 in front, all right, to make sure that the comparison's easy. Oh my goodness, 5 compared to 0. Okay, well, this one's a bit more obvious. All right, 51.34% versus 4.55%. Pretty clear which one is bigger. Now, to compare fractions, okay, if we're asked to do that, well, this is kind of easy. Convert to a decimal and then line them up. Okay, so we follow the procedure that we've been doing, only we have one additional step. So 1/7 and 1/8, we compute that on the calculator, 1 divided by 7 and 1 divided by 8. You'll notice one decimal keeps going with the ellipsis, the other one stops. We line them up, put a 0 there. And we notice the comparison comes to the second digits in the place value, the hundredths, okay? Clearly as 4 is more than 2, okay? So this would imply then that 1/7 is the larger of the fractions. Now we have an application of comparing decimals, all right? So let's understand this. For each pair of numbers, tell which is closest to the number given in parentheses, all right? So this is something you're going to need to be able to do. So let's suppose we have 1.78 and 1.85. Which of these two is closest to 1.80. So how do I figure this out? We use subtraction, okay? We always take the larger number minus the smaller number. So we have to do two computations for the subtraction. So the first is going to be 1.80 minus 1.78. So that's the first number that I'm looking to compare. That difference is 0.02. The next one we take is 1.85 minus 1.80. And what we get is 0.05. You'll notice in both of these cases, both of these subtractions we've just done, these subtraction problems, we've used the 1.80 because that's the number I'm interested in. I want to know how close am I to that. Well, we notice that the two differences are 0.02 and 0.05. We want the difference that's smallest because that's the number that's closest. So in this case, 1.78 has the smaller difference. So it's the closest to 1.80. Let's suppose we have 0.1309 and 0.1289, and we are trying to figure out which is closest to 0.1298. All right, we make the comparison. So we take the first number, okay, 0.1309, and we subtract the number in question that I'm trying to figure out how close are we to, and we get 0.0011. Then we do the same thing with 0.1289. Okay, and it's always the larger number minus the smaller number. So we have 0.0009 is that difference. So which of these two differences is the smallest? Well, 0.009 is smaller than 0.0011. You could line them up, okay, just like we did a few minutes ago. And what that would tell you is which one is the largest. We're now interested in the largest. We want the smallest. Smallest difference means it's closest to the number in question. So in this case, the 1,289 10,000ths is closest to the 1,298 10,000ths. Our next segment is going to deal with operations, and this is an important one because in this class you're going to have to do some computations, okay? So we'll start out easy and gradually work our way up, and for sure you're going to be able to use your calculator, so I would recommend having your calculator out for this particular segment. Now, before we get into the nitty-gritty of actually some examples, I want to draw your attention to a few preliminary things. So first of all, we always deal with four main operations: addition, subtraction, multiplication, and division. So in this class, in statistics, you will be asked to use these operations to determine answers to problems, but sometimes you might be asked to combine the operations. We therefore need to use our good friend, the order of operations, to help us establish a process for doing this. Okay, now the order of operations is the parentheses exponents, multiplication slash division, addition slash subtraction. Many people remember this as PEMDAS. This is a little problematic, okay, because we have to be careful with multiplication and division and addition and subtraction. So when people think of PEMDAS, they think that multiplication always comes before division. That's not always the case. They also think addition comes before subtraction. This is not always the case, okay? Popular to the contrary belief that exists out there in social media, especially with these order of operations questions. So we will work a series of problems where you may be asked to combine the operations, and if so, you're going to have to use the order of operations. So we'll examine the operations using fractions and decimals. You have to be familiar and comfortable with those. And you want to make sure that you do pay attention to directions of a problem, since it might ask you to express the answer as a simplified fraction or a decimal rounded to X places. X could be any number, 4 decimal places, 3 decimal places, etc. So we have to be careful. Make sure you read those directions carefully. Now, before we dive in, we do need to remember that these are algebraic expressions, not equations. We're not dealing with equations here. So the equal sign and how we use it indicates the next step in the computation. So please be careful with how you're using the equal sign. Your calculator is very useful here, and I will try to emphasize as much as possible what you should be entering into your calculator to make it easy on yourself for the computations, because I know everybody might be using different kinds of calculator with different capability. So I'm going to do this for the most basic calculator, such as one on a cell phone or a simple calculator itself. Now, the path shown to getting the answer may not be the only way to get it. Okay, so what is being shown here might be the easiest or what makes the most sense for using the calculator. All right, so please don't get stressed with me. Why is he taking us through all of these steps? It's much easier if we just do this, this, and this, and we get an answer. Hey, if you can do it that way, that's wonderful, but not everybody has the same capabilities that you might have. And of course, throughout the computations, I want to just emphasize, please don't round anything during the computation. Keep as many decimal places as you can. Only round at the end of the problem to whatever the directions indicate. Okay, now people might be wondering, well, why don't we want to round when we're doing the computation? This can do what we call skew our answer. So in other words, it makes the answer not quite as accurate as the one that the homework might be looking for. So try to keep the rounding until the very end. Keep as many decimal places as you can during the computation. Okay, with all that excitement out of the way, let's do some examples. So to add or subtract fractions, you can do this in two ways. Number one, convert to a common denominator, or CD, or convert to a decimal and use your calculator for that. So here's an example, 3/8 plus 1/7. Way number one, get the CD, multiply the two denominators together. 7 times 8 is 56, okay? What this means is we need to convert 3/8 and 1/7 to 56. We know how to do this because I covered this in an earlier segment. So hopefully you remember how to multiply by a form of 1. So there they are, 3/8 and 1/7. Okay, 2156, 856. We add them up. We get 2956. Pretty straightforward. Okay, so getting a common denominator, just simply multiply the two denominators and then convert each fraction, okay, to that particular CD by multiplying by a form of 1. And then you add the numerators. Simple as that. Now, if you want to use the calculator, what we need to do is convert each to a decimal. Okay, so 3/8 is 3 divided by 8, which is 0.375. Then we have 1/7, 1 divided by 7, 0.142857. You notice the ellipsis, which means it keeps going. Okay, we add the two decimals and you get 0.517857, and you notice the dot, dot, dot. It keeps going, okay? Now, there were no instructions on the rounding here, all right? So that's why I kept it to as many decimal places as I can. Again, on the homework, we would tell you to round to a specific place value. So make sure you pay attention to that. But in this case, I kept the 6 decimal places as I'm following my own advice. This is a good example to all of you. Okay, how about this one? 13/15 minus 5/15 plus 6/15. So how do we deal with this? So in this problem, all of the denominators are the same. So we don't need a common denominator. Life is great when this happens. And you know what? Sometimes it will happen in this class. So there's some good news. There's some optimism, some things to look forward to in statistics. Now, notice that we have both addition and subtraction, but subtraction's first. So by the order of operations, since both addition and subtraction are consecutive, in other words, it happens one after another, we must take them in the order they come. So subtraction is first. Okay, so all of you who are watching this idea of PEMDAS and addition has to be first, it's wrong, okay, if you have the two operations, addition and subtraction, happening consecutively like we have here. You have to subtract first, okay? You have to subtract first. So make sure you are very careful with my order of operations. So here's our problem, 13/15 minus 5/15 plus 6/15. We first focus on the subtraction, since that's what comes first in this, with addition and subtraction coming consecutively. Okay, so what is 13/15 minus 5/15? Well, that's 8/15. Okay, now the question happens, what happens with 6/15? Well, it falls down. Okay, we can only combine two numbers at a time here. All right, now we just simply add. Boom, 14/15. As a decimal, just in case anybody's wondering, 0.9333 or 0.9, and you'll notice the 3 is what's repeating, okay? And if we round this to the nearest thousandth, it would be 0.933, just to give you a little bit of context, just in case the directions ask you to do some rounding here. To multiply fractions, simply multiply straight across and then simplify as needed. So if you're asked to express the answer as a decimal, convert the final answer to a decimal and round as needed. Okay, so if we were asked to compute 8/13 times 3/4, okay, we want to express the final answer as a simplified fraction or decimal rounded to 4 places. This is something you might see in your homework, okay? How do we do this? Well, very simple. Here are the two fractions. We multiply straight across. 8 times 3 is 24. 13 times 4 is 52. Now, 24 over 52 can be simplified. How do I know that? Well, both of the numbers are even. Numerator and denominator are even. As a matter of fact, it's 4, okay, is the factor that both numerator and denominator have in common. So there's that form of 1. And what I'm left with then is 6/13, okay? 6/13 as a decimal, 0.461538. My directions say round to the 4 decimal places. I look at the 4th decimal place, I see a 5. Okay, I look at the digit to the right of that, which is 3. 3 means the 5 stays the same. So the answer here is 4,615 10,000s, okay, 10,000s. Now, to divide fractions, we have to multiply by the reciprocal. There's an interesting word. And then the problem follows the steps that we just had on the previous slide. Okay, so there's a little bit of a first step, okay, to sort of modify the problem. Now, what is a reciprocal? The reciprocal of a number is called a multiplicative inverse. So to find a number's reciprocal, we quote unquote flip it. Okay, what the heck does this mean? Here's a few examples. 7/8, its reciprocal is 8/7. Do you see what's happening there? The denominator goes into the numerator and the numerator becomes the denominator. This does not discriminate, this process, if you have a negative sign. In fact, the negative sign just comes along for the ride. Okay, so -14/3 is the reciprocal's -3/14. What about 5? Okay, well, we need to convert 5 to a fraction. That's easy, 5 over 1. We flip that, we get 1/5. Okay, and then you see another example there with a bigger number, 1,843. The process is pretty much the same. So let's put this to use. There we go. 7/5 divided by 1/3. All right, well, to complicate your lives, this is called a complex fraction. Why? Well, the numerator and the denominator are both fractions. So we call it a complex fraction. So how do we deal with this? Okay, no big deal. So we'll have to express the final answer as simplified fraction and decimal rounded to 4 places. Okay, we get that. To do this problem, we multiply by the reciprocal of the denominator. So we have to do a rewrite. So 7/5 divided by 1/3 becomes 7/5 times, and we multiply by the reciprocal of 1/3, which is 3/1. Then we multiply the fractions. How? Straight across. Okay, so there's my reciprocal, 3/1. So we get 21/5. We could write this as a mixed number. That sometimes is easier, 4 1/5, okay, because then the fraction is now simply 1/5 to convert, which is going to be 4.2. We put some decimal places there because the zeros, we had to round this to 4 decimal places. So we didn't have enough, so we had to put some zeros there as the placeholder. And that's what we end up with. Okay, suppose we're asked to multiply 11 times 47 over 33. Okay, simple enough. To multiply fractions, we multiply straight across. So first thing I need to do is convert 11 to 11/1. Multiply straight across. We get 517 over 33, which simplifies to 47 over 3. And as a mixed number, that's 15 2/3. How did I get that? Used long division. Okay, we covered this in an earlier segment. So pretty straightforward. Now, we're going to look at some problems next that you may encounter. And I don't mean in the literal sense, at least the structure. Okay, so as you look at these, you're going to say, well, you know what? I remember doing this in the math review, and that's good. Okay, so this is something that you might see in later on in the actual content that we cover in this class. So the first example here is 4.29 divided by the square root of 131. And we want to round our answer to 4 decimal places. So how do we handle this? Okay, well, first of all, we can definitely use the calculator on this. Okay, that's going to be a useful tool here. Now you'll notice we've got a square root. Okay, this can be thought of as a grouping symbol, like parentheses, if you're thinking back to order of operations. So what we need to do is actually take care of the square root first. By take care of, I mean figure out what is the square root of 131. So that's what we did. So you notice the 4.29 stays in the numerator, and in the denominator, the square root of 131 is 11.44 and a bunch of decimals. Okay, keep as many decimals as you can. Then you do the literal division on the calculator. 4.29 divided by this 11.44552314. This gives us 0.374819. Okay, and I needed to round to 4 decimal places. Okay, well, the 4th decimal place would be the 8. To the right of that is a 1. The 1 means that the 8 stays the same. So we have 0.3748. Okay, so hopefully a relatively straightforward computation. So take this just one step at a time. Do the square root first, write that number down, then do the division with the numerator. Okay, here's another one. So we have 76 minus 78, and we want to round this to 2 decimal places. So what you'll notice is we need the order of operations, okay, because we're dealing with a fraction. So we need to make sure both the numerator and the denominator do not have any operations in it. In other words, they're fully simplified. It's a number over a number. What you'll notice is we don't have that here. If you look carefully at the numerator, I have 76 minus 78. I have to do something with that. If you look at the denominator, it says 1.713. Okay, well, there's nothing I can do with that. It's in its most simplified form. So what I do is I first do the 76 minus 78. That's -2. Okay, and then we divide that by 1.713. How do we do that? We use our calculator. And so what that comes out to is -1.1675. Rounding that to the 2 decimal places. Well, the 2nd decimal place is a 6. We look to the right of that, we see a 7. That's more than 5. So that 6 becomes a 7. So we end up with -1.17 in this particular case. Okay, so when you're dealing with fractions, sometimes we have to do a little bit of manipulation, simplification in the numerator and or the denominator. Here's an interesting one. So in this expression, we're adding and multiplying 4 times. Okay, so got to use the order of operations. Okay, well, the good news, the order of operations is very clear. Okay, it says we have to do the operation of multiplication first. All right, so fortunately, we can use the calculator. All right, so what do? Well, you take 21.5, we multiply that by 5, and you get 10.5. Okay, 1.39 times 6, 8.34. 1.98 times -3. Did you all see the negative there? Be careful. Got to watch your signs. Okay, that's why that -5.94 is in parentheses. Be careful. 1.1 times 4, 4.4. Now that all the multiplication is done, we just simply add it up. Okay, now before I do that, you notice I did a quick rewrite here, and the rewrite came with that plus a -5.94, that becomes subtraction. I'm actually subtracting that 5.94. So be careful when you have negatives pop up in that. In this particular instance, since we have addition and subtraction and addition occurring, you have to work them left to right since it's occurring consecutively. So I do 10.5 plus 8.34. Then I subtract 5.94, and then I add 4.4. So you move left to right each of these computations consecutively, and you come up with 17.3. So please be careful with your negative signs. Very, very easy to lose track of those. Now, another aspect to order of operations is formulas, okay? Now, in this class, we do have a formulas sheet, okay? So what we're gonna teach you is how you know when you have to use those formulas. And so you're gonna have to be able to obviously not only choose which formula to use, but also run the computation, okay? So that's what this particular segment is going to be about. Actually, how do we substitute values into the formulas and then actually solve? So some of the formulas you see in the course, we're actually going to dabble in and work with in this particular segment, which is fine, okay? But for now, I know you're going to see a lot of variables, so don't panic. We'll cover what those variables mean during the class. For now, it's just going to be about substituting and focusing on how do I use the order of operations to figure out what my answer is. Okay, so here's the first formula. The first formula is the square root of p times 1 minus p all over n. Okay, again, we don't care what p and n are, literally. We'll learn that in the statistics course. For now, we just know p is 0.8 and n is 120. And what we need to do is round this thing to 4 decimal places. Now, what this is a formula, and we have to make some substitutions here. Okay, so we have to correctly substitute the values that we are given. So what you'll notice is that for p, I put 0.8, and for n, I put 120. All right. Now, we have to use order of operations, okay, to figure out what exactly we need to do. Well, if we look inside of the square root, there are 2 things happening. I've got a fraction, okay? The numerator of the fraction has 2 things going on. One is a subtraction problem and the other is multiplication. And the denominator is 120. There's nothing I can do with that, so it's good. So the denominator is ready to go. So what we do is we first use order of operations, which says take care of the parentheses. So we do 1 minus 0.8 and we get 0.2. Then we do the multiplication. So 0.8 times 0.2 is 0.16. So we take 0.16 divided by 120. Okay, that gives me 0.00133333 ... We take the square root of that, and we get 0.0365148. We round that to 4 decimal places. The 4th decimal place has a 5. We look to the right of that, which is a 1, so the 5 remains the same. Okay, so half the battle here is correctly plugging in the number, and then the other part is running the computation, Okay, here's another formula. We have O minus E, quantity squared, divided by E, okay? And we have our values for O and E, and we want to round the final answer here to 4 decimal places. Okay, so we correctly substitute. So 98 here is O, and the 101.439 is in for E. Now you'll notice again, we're dealing with a fraction, and the denominator of this fraction is simplified. There's nothing else that I can do with this, but the numerator has some stuff that I need to do. Okay, so we've got a parentheses, we've got an exponent, we have a subtraction. So I need to take care of what's in the parentheses first. So I need to do the subtraction, okay? Now we have to be careful because sometimes people get tempted to distribute that exponent. And so you'll notice the warning that I have here. You can't distribute that. That exponent does not distribute over subtraction. So please don't fall for that, okay? Very, very tricky, very, very easy mistake to make, and one that is disastrous, at least in terms of the computation. So please be careful. Okay, so what we do then is we take 98 minus 101.439 and we get negative 3.439. That's what's going to end up getting squared. Okay, so that's the next thing you do is just square that. And we end up with 11.826721. We divide that by our denominator and we end up with 0.116589. We take that and we round to 4 decimal places. We've talked about how to round, so the answer here is 0.1166. The next formula is P times the quantity of 1 minus P times Z over E, quantity squared. Okay, and our values for P, E, and Z are given. All right. So here we go. We make sure we substitute correctly for P, Z, and E. So there they are. And next we need to make a determination of how do we do this with order of operations. There's quite a bit of stuff that's going on here. Okay, so here's what I did. I took 1 minus 0.74 and I got 0.26. Okay, so that's a pretty easy subtraction to take care of. All right, since order of operations does tell us to take care of parentheses first. So that's what I did. You'll notice the other parenthesis we had was 1.85 divided by 0.001. Okay, in this particular case, the fraction is simplified. There's nothing I need to do in the numerator and the denominator. There's no operation. So I just go ahead and divide them. And what I end up with is 1,850. The next step is to square the 1,850, because that's what the order of operations tells me I have to do first, the exponent, okay? And I get this 3 million number. Now I multiply. You'll notice it's three numbers being multiplied together, so I just simply work left to right. So I multiply 0.74 times 0.26 and get 0.1924 and multiply that by the 3 million, and we end up with 658,489. So this one looked a little tougher. Just make sure you're following the order of operations and you do the computations one at a time, just like I did. Record each of the steps. This is called showing your work, something that is very important that you need to do in your statistics class. Okay, how about this one? Okay, so in this example, there is a formula, believe it or not, that would give us this sort of a result, okay, maybe with different numbers. But we need to round this to 3 decimal places. So how on earth would we handle this craziness? Well, what I would look to do is to try to simplify this as much as I can. So if you notice, the numerator is a simple subtraction problem, 0.24 minus 0.231. So I plug that in the calculator and I end up with 0.009. Then I look at the denominator. Okay, now the denominator is this massive square root. So the first thing that I do in the square root is I take care of the parentheses, because that's what the order of operations tells me I need to do. So I do 1 minus 0.231, and I end up with 0.769. Then what I need to do is multiply 0.231 times 0.769. Okay, I'm trying to simplify that fraction underneath the radical. So that result is 0.177639. Then I can finally divide that by 57, and that's the number you see in the square root now, 0.0031164737 ... Bit of a mouthful to say. So what we do next is we actually take the square root. If you remember, this phase of the problem now, this simplified form, is actually similar to an example that we just did at the beginning of this segment, where it was a number over the square root of a number. So you have to take the square root of the number. And you see the result there in the denominator, 0.05582, etc. Well, we divide that into the 0.009, and what we end up with is 0.1612169. Rounding to 3 decimal places, 0.161. So yes, you will need to be able to do computations like this. There is a formula that will produce this particular result. So this is a typical thing that we'll actually be looking at a little later in the course. And we conclude this segment with this wonderful example. So we want to round this to 4 decimal places. All right. So we've got a numerator, a denominator, and then the denominator, there are 2 radicals, there are 2 subtraction problems, and 2 exponents. So what on earth am I doing to you? Okay, well, let's simplify this really easily. So you'll notice in the numerator, I did 8 times 4 and 2 times 3. That gives me 40 minus 6. Pretty easy to take care of. In the denominator, according to the order of operations, it says you need to do the exponent first. So that's exactly what I did. 3 squared and 4.1 squared are 9 and 16.81 respectively. The next thing I did was a whole bunch of subtraction. So I did 40 minus 6 in the numerator, which is 34, 36 minus 9, which is 27, and 41 minus 16.81, which is 24.19. Then what I did is I took the square root of 27 and the square root of 24.19. Then I took those 2 results and multiplied them and got 25.5564082. I divide that into 34 and we end up with 1.33039, rounded to 4 decimal places, 1.3304. So this thing might look very menacing, but if you use the order of operations, it really can be a very simple process. So take your time, work the computations carefully, and write down each result as you go. Our next segment deals with solving equations and formulas. So there will be some instances where you might have to do some manipulation with equations or formulas. So how does this work? To solve any equation, we need to try and isolate the variable. That really is the whole point of solving an equation. We need to isolate the variable. Okay, so this means that we need the variable on one side of the equal sign, everything else on the other side. So it doesn't matter, it could be all on the left or the right, just as long as one side has the variable, the other side, all the other stuff. So the process for solving an equation varies depending on its type, okay? So here's a few hints to consider. Number one, clear any fractions by multiplying by what's in the denominator. Clear any decimals by multiplying by the place value in the rightmost decimal. Think about the inverse operation in an equation to help you, quote unquote, undo the operation you are dealing with. And whatever you do to an equation, please do it to both whole sides. So let's see this at work. So to solve this equation, 7 minus 2/3 x equals 5, here's the process. Okay, I'm first going to clear fractions by multiplying both sides by 3. Why 3? Well, that's what I see in the denominator. So here's what that looks like. Notice on the left side, I'm using parentheses. Very, very important as a grouping symbol. This shows it's being multiplied by both whole sides. And on the right side, we have 5 times 3. So we have to distribute the 3 on the left side. So what that looks like is 3 times 7, which is 21, and then 3 times negative 2/3 x. And what you should notice is that the 3 is going to go away or simplify with the denominator of 3. So that leaves us with negative 2x. Okay, so now this equation is much simpler. 21 minus 2x equals 15. Now what we can do to isolate the x is simply subtract 21 from both sides. There it is. So the result is negative 2x equals negative 6. Notice we kept the negative 2. That's important. Some people drop that negative sign. It has to stay with the negative 2x. Now what we can do is divide by negative 2. And my result is x is equal to 3. So that's a process for solving at least one of the more complicated equations that you might have a tendency to come across. Now, what's nice is you can always check your answer by simply plugging the 3 into this equation and solving, and both sides should come out to be the same, 5 in this case, and you're welcome to check that on your own. So here's another example. This one says 82 is equal to, we have a rather complicated rational expression. There is an x in there, if you read very carefully, 98 plus x plus all these other numbers divided by 7. So we have a fraction. So what I'm going to do is multiply by the number that I see in the denominator, which is 7 in this case, to clear the fraction. Again, notice my use of parentheses. So 7 times 82 is 574. And you notice on the right side, all of the denominator went away. So I'm just left with this giant expression that I'm adding. So that's what I did. I added all the numbers up and I got 503 plus x. Now it's real easy. Simply subtract 503 on both sides and we get x is equal to 71. So this really long, complicated looking equation really wasn't so bad. Now, if we change the game on you and ask you to solve a formula, okay, well, it really is kind of the same process as solving an equation, okay? Now, a formula can be considered an equation, only instead of having one variable, there might actually be several variables. Hence, we call it a formula because each variable stands for a specific value. So to solve a formula for a specific variable, we want to treat the other variables as numbers and solve like you would an equation. So let's look at an example. Z is equal to x minus x bar divided by sigma. And what we want to do is solve this for x bar. Okay, so x bar has a little bar on top of it, different than x. So what I'm going to do is I'm going to treat z, x, and sigma as numbers. So my goal is to get x bar by itself. So I want x bar equals something. So what I'm going to do is I'm going to clear fractions. So I'm going to multiply by sigma on both sides. So on the left side, that leaves me with z sigma. And on the right side, the sigmas are going to go away. And what we're left with is x minus x bar. Now, remember, I'm solving for x bar. So I'm going to subtract x on both sides. So that leaves me with z sigma minus x is equal to negative x bar. So I don't quite have x bar by itself. So what do I need to do? I need to either divide or multiply by a -1. And so I chose to multiply by a -1. So that's going to make the x bar positive. Notice the parentheses that I'm using on the left side. Very, very important. So then I distribute that -1. I get negative z alpha, z sigma plus x, because -1 times -x is a positive x. Negative times a negative is a positive. And there's the formula. So we get x bar is equal to negative z alpha plus x. And you notice in this case, I chose to keep the variable on the right side, which is perfectly fine to do. So this concludes the discussion on solving equations and formulas. This next segment is on set theory and specifically looking at the intersection and union of sets. So this is very important, especially as it relates to probability. So a set is a collection of objects we can think of as in an abstract container. And we generally use capital letters to name our sets. So here's an example. We have the set A, capital A, is equal to 1, 2, 3, 4, 5, and then the lowercase ABC. So this is an example of a set. So we use those fancy brackets to denote the abstract container. Now the objects in the set are called elements. So in this case, the notation we use is 1 is an element of A. Okay, and the reason is because the number 1 is in that set. I can point it out to you. The other one we have is 11. Okay, 11 is not an element of A. If I look at the set capital A that's on the screen, I don't see now the number 11 anywhere there. Okay, so that's how I know it's not in the set. So that's a little bit of the notation that we tend to use. Now, there are generally two things we want to do with sets of objects. One is to put them together, and the other is to see what exactly they have in common. So is there anything in common between the sets? Now, when we put sets together, we generally call this their union. And if we're looking for what they have in common, we call it an intersection. So we have to know the difference between them. Union, we put stuff together. Intersection, what they have in common. Now, the notation that we use is this U symbol that denotes the union of a set, and the word or is associated with this. We have the upside down symbol, okay, of the union symbol, so it's the upside down, denotes the intersection of a set, and the word that we typically use here is and, okay? So you wanna make sure you're paying attention to or and, very important. So or goes along with union and with intersection. So given the following sets, let's find the following. So we have set A, set B, set D, and set D. Let's see if we can make sense of this. So the first we have is the union of A into B. So find A union B. So what exactly is this going to look like? Well, the union is what's in either set. So in other words, we put the two sets together. Okay, so here's what it looks like literally. So set A is the elements A, B, C, D, E. And set B is the elements C, D, and F. So when we put them together, we get A, B, C, D, E, F. Now, some people say, do we have to put the elements that are repeated? Do we have to put C twice, for example? The answer is no. So we only write them once. So the union here is very simply A, B, C, D, E, F. Just combine them. The next example is to find D intersect B. Okay, so intersection means what the two sets have in common. So D intersect B. So set D is the elements A, D, G, and N, and we intersect that with set B, which is C, D, and F. So what do the two sets have in common? The answer here is the element D. So this is the set of D. So the answer is not just the letter D. We have to make sure we use the brackets. Very, very important, okay? Because the answers to these are sets. So using those brackets is essential. So in this case, they only had one thing in common. Let's suppose we asked you to find C intersect B. Okay, so what do we notice? Well, C is the set of G, H, K, and whoops, I mixed up my symbols here. So that should be an intersection, not a union. Sorry about that. So intersecting with C, D, F. You'll notice that the two sets don't have anything in common, nothing. So that's why the set's empty. As a matter of fact, we call it the empty set. So these two sets have nothing in common. So the answer is the empty set. Now, this is actually a little phenomena that sometimes will happen in which we call the intersection empty. And what we say is that the two sets are mutually exclusive. In other words, Sorry, they don't have anything in common. They have nothing to share, nothing between them. So they are in fact mutually exclusive. So you may see that if the intersection is the empty set, nothing in common, we call them mutually exclusive. All right, the next segment that we have is translating English to mathematics. This is a short one, I promise. Now, this is an important set of skills that you're going to need a little later on in the course, specifically when you have to do some understanding of the written component of a problem, and we need to actually write some sort of an expression in order to help us to understand a little bit more of the statistics. So you will have to read a problem and then construct an algebraic expression. So we have to make sure that we read carefully and identify the key phrases that can easily be translated to math. Okay, so when you're reading these problems in the statistics homeworks, make sure you look for the phrases that we are about to talk about as presented in this wonderful chart. So what is bolded and underlined here are the key phrases. Okay, so if somebody asks you in a problem the sum of 92 and 3, what does that mean? That means 92 plus 3. The difference between 5 and 19, that means 5 minus 19. 37% of 9,329. The word of means multiplication. The word of means multiplication. A number is more than 17. So let's let the number be X, because I don't know what it is. Could be Y, could be Z, whatever variable you want. In this case, we'll use X. Okay, so a number is more than 17. This means greater than. So a number is at most 2,390. What does this mean at most? Well, that means that's the largest that it could be. Okay, so the number, the X could be the number X less than, it could be less than or equal to. So there could be a little bar underneath that inequality. So X is less than or equal to 2,390. A number is at least 31. Same thing. I could be 31 or more. So this could be X is greater than or equal to. So that little bar underneath the greater than sign could be there. X is greater than or equal to 31. So at least means more than. A number is less than 3.7 and more than 1.2. This is an interesting looking inequality. This is actually called a compound inequality. So what this tells me is that the number is actually between 1.2 and 3.7, because I can be simultaneously more than 1.2, but less than 3.7. So that means the number is between the two. Right, because if I chose a number of 3 is more than 1.2 and it's less than 3.7. So it satisfies both of those conditions. The next one is a number is at least a half or at most 1/7. So if it's at least a half, that means it's more than a half. And if it's at most 1/7, this means that it is less than. Notice the word there, it's or. Okay, can't be both. I can't be simultaneously more than a half and less than 1/7. That makes no sense. So the word there is or. And then finally, a number is not 23.3421. Well, that's pretty simple. X is not equal to this particular value. So these phrases you may see, okay, come up in the discussions a little bit later on in the course. So again, with at most and at least, you could use the equal to in the inequality. It just depends on what the context is. So do make sure that you're reading carefully. In most cases, we do say X less than or equal to or X greater than or equal to for at most or at least respectively. So that's translating English to algebra. The final segment, welcome to the final segment, deals with the XY coordinate system and equations of lines. So let's try to understand how this is going to work. Well, here's our XY coordinate system. So hopefully you may have some memory of how to use the XY coordinate system. So a few background pieces of information. So this is based on a coordinate system, okay? We have two axes. So there's an X axis and a Y axis. So the X is the horizontal, the left to right. The Y is the vertical, the up and down, okay? And they're labeled in the diagram at the right. We use points X and Y to plot on this system, okay? So the XY is sort of the location, if you will, in the coordinate system. Taking infinitely many points together, we're able to create things as lines and parabolas and all sorts of cool looking graphs and pictures, if you will. Okay, but it's the key here is infinitely many points together. So when we start to graph as many of those, then it starts to look like something, a line, a parabola, etc. Now, to understand the XY coordinate system, we have to remember how we plot points, okay? So plotting points in this system is actually very easy. So a couple things to remember though. The X coordinate controls the left and right movement. Okay, so the X coordinate tells me left or right by how many units. The Y coordinate controls the up down. All right, so an example is 4, 5 means we would move 4 units to the right and then 5 units up. Okay, how do I know that? Well, both are positive. Okay, if you have a negative, then negative 3/4 means we would move negative 3/4 units to the left and 0.7 units up. So it doesn't have to be exactly an integer. It can be fractions or decimals. That's perfectly fine. And in which case you'd have to approximate where it would be on the coordinate plane, which is fine. You'll notice in the diagram on the right, we have 3 examples, actually 4 examples. We have 0, 0, which is known as the origin. Okay, we have the point 2, 3 in green. So this means you move 2 units to the right and then up 3 units. The one in red is negative 3, 1. So you move 3 units to the left and then up 1 unit. And then the other one, interestingly enough, is negative 1.25 comma negative 2.5. So we move negative 1.5 units to the left, and then we move down negative 2.5 units. Okay, so that's the idea behind plotting points. The next piece to this is dealing with equations of lines, okay, or linear equations are given by this common formula, y is equal to mx plus b. You may have seen this before. This is known as the slope-intercept form. So the slope is the variable m. This is known as the rate of increase or decrease as the line moves 1 unit to the right. Okay, so slope controls sort of the steepness of the line. In other words, how it increases or decreases. So it can be thought of as a rate. A positive slope means the line is going to go up if you move left to right. And if it's a negative slope, it means the line is going to go down as you move left to right. So it can be positive or negative. Could be 0 too. 0 means it would be flat. And B is known as the y-intercept. The y-intercept is the point where the line crosses the y-axis. And it's often written as this ordered pair 0, comma B. Okay, 0, comma B. So it's the point where we cross the y-axis. So here's an example. Y is equal to 72.2 minus 0.82x. Okay, so the y-intercept here is 72.2. How do I know that? Well, it's not attached to the x, okay, not attached to the variable. So the literal y-intercept is 0, comma 72.2. The slope here is negative 0.82. So you notice we need to make sure we capture the sign. And here's how we interpret it. It says as we move 1 unit to the right, the line will decrease by 0.82 units. So this means that the line is actually coming down as we move left to right. Now let's suppose that I tell you that m is negative 7/3 and we have 0, negative 4 as a point on this line. Give the equation for the line with this slope and the point. Okay, well, first of all, we know the slope. Very clearly stated as m is equal to negative 7/3. Can't make that any more obvious, but we need to figure out what is b. Now, if we look carefully at the point that's given, it is given to us in the y-intercept form. Remember, that's always 0, comma b. Look how it's written, 0, comma negative 4. So b here is negative 4. So when we write this out as y equals mx plus b, what we end up with then is y is equal to negative 7/3 x, since that's the slope, minus 4, since that's the y-intercept. And you'll notice that I did write it in the other way. You can reverse the order. Make sure you keep the signs. Both are negative in this case. Negative 4 minus 7/3 x. The last thing we're going to look at is how to graph a line. This is pretty simple. Okay, to graph any line, you simply plot 2 points. And there's good news. We get one of the points for free. What is that point? It's the y-intercept. So to get the second point, you can plug in any value you want for x. That's the great news here. Plug in any value you want for x, anything you want. Try to stay simple though. Once you have both points, you plot them and then you connect them. So let's look at a simple example. If we have the line, the graph rather, y is equal to -4 plus 0.3x, we wish to graph this particular equation, we notice that b is -4, so we have a y-intercept of 0, -4. So I'm going to go ahead and plot that point. So in this particular instance, the x-coordinate is 0. This means I don't move left or right. So I'm still locked in at 0. So I'm right along the y-axis. Then what I do is I have to go 4 units down for -4. So I'm going to end up right here. Then what I'm going to do is I'm going to plug in a value for x, any value I want. So I chose 2. Okay, so when we plug that into the equation, what comes out then is -3.4. So my point is 2, comma, -3.4. So 2 means I go 2 units to the right on the x-axis and then down -3.4. So somewhere about there. Now, there are my 2 points. Now what I do, I connect them. And so there's my line. Now, what you should notice is that this line goes up as we move left to right. This coincides with the slope of 0.3, which is positive. So this is how I know I've got the right graph, because if the graph was going down and I see a positive slope, then I made some sort of computational mistake. So pretty easy to see in that respect. And I have more good news. That is it. So thank you for surviving all the way through the math review concepts for elementary statistics.